presentation has been brought to you by 60 East Midlands and ASHRAE UK Midlands chapter. I'm Shazia Dixon. I am the current serving president for the UK Midlands chapter. And we are delighted to have Drew Crawley today from United States here at Loughborough University. And we are really living in very exciting and challenging times with net zero emissions by 2050 targets are looming ahead of us. And UK is one of the major economies that made it into law. And as we know, buildings account around 40% of the energy-related gas house emissions. And therefore, decarbonizing the new buildings and also existing buildings, it really creates an extreme challenge for all of us. And by 2050, 68% of the world's population will be living in cities, doubling from today's numbers of 4.4 billion people. And cities will play an increasingly important role tackling climate change. And Dr. Crawley's presentation will look at impacts of climate change and urbanization on future building performance. Before I introduce you to our speaker today, so today's session is being recorded, so it will be available online on the YouTube channel. And please, if you are listening online, kindly mute your microphones throughout the presentation. And we will hold a Q&A session at the end. And we will alternate between people here we got in the lecture room and the people on the online. And use your microphone. If you put your hand up, and then you can use your microphone, or you can write on the chat box. And so we will probably have at the end around 10 to 15 minutes of Q&A session. Just going now, introducing our speaker. Well, thank you very much for coming and seeing us, Dr. Crawley. And he is a globally recognized authority in building energy analysis field and renowned throughout the green building field for leading the development of the US Department of Energy's Energy Plus simulation engine. Under his leadership in the development of the Energy Plus engine has resulted in this technology becoming the standard of the industry. He is also referred as father of Energy Plus. This year, Dr. Crawley received the International Building Performance Simulation Association US Award for Distinguished Achievement in Building Simulation. So please welcome Dr. Drew Crawley.
Thank you, and I'm very happy to be back in Loughborough. Always a pleasure to be here. My external examiner for my PhD is sitting right back there. So, and he did not make it easy for me, I can tell you that. But that's good. That's good. I'm going to very quickly go through some of the things I found on climate change and urbanization and new information that's happening. To give you a kind of a feel for what's going on. As mentioned, this is a distinguished lecture program, the ASHRAE program that brings lectures to chapters. And so I get my way paid to come visit here, which is, I think, an incredible program. I don't know of any other professional society that does that. ASHRAE, if you're interested in becoming a volunteer, ASHRAE is always looking for opportunities for that. And they have amazing training programs for young engineers. The young engineers in ASHRAE is a great way to learn about the society and get involved. I've been involved in many of these technical and standards committees over the years. I'm not going to give you that. If you need continuing education credits, this counts. I always like to start my presentation by talking about why do we care about energy in buildings. Buildings globally are responsible for about 30% of energy use, 37% of carbon. And so we have a kind of an enormous share of that. And you see it varies quite a bit. If you look at the third and fourth bars, China and Hong Kong are kind of the two extremes. where China is under 20% for buildings recently, and Hong Kong is 65%, and with very little industry there. When I started doing this sort of chart 15 or so years back, China was at 10% for buildings. That massive growth has happened just in the last 20 years, and it's continuing, and it will continue around the world. It's estimated by 2060, we will be doubling the amount of floor area built globally, which is the equivalent of building a New York City footprint, every month, which is huge. So it varies quite a bit depending on whether the economy is more focused on industry. UK is kind of in the middle, as is the US, with buildings taking on a larger role for them. Just to give you kind of an idea, buildings are 40% in the US, split roughly between residential and commercial. And I bring this up because I think it's important to understand our buildings are no longer simple. They have become more complex. Heating, water heating, cooling, depending on where you are, all very important. But we have all our appliances, computers are now accounting for 1%. But it's this new thing that's happening, the 25%, that's really beginning to drive industry. It's all our little devices that are really beginning to change how that's doing. So we have to deal, if we're going to make our buildings net zero, we have to deal with all of it. We can't just deal with the easy fixes there. Same is true on the commercial side. This is average across the sector, but almost a full third of the energy is related to many small devices and other end uses that are not showing up there. But for example, if you're a supermarket, that refrigeration number would be 50%. It just far dwarfs anything else, cooling, lighting, anything else related to the building. If it's an office building, you're going to see the ventilation, the lighting, and other taking part of that. So weather is not the same as climate. I have a joke I just heard from a 6-year-old, so please take it in that. Clara says, what's the difference between weather and climate? You can't weather a tree, but you can climb it. So it's 6-year-old humor. But anyway, that's from Carrie Brown, who's president of BIPSA USA. So weather is what's happening right now. It's the wind, the temperature, everything else. But climate is the long term, looking at that. So when we talk about climate change, we're talking about a long-term view of what's happening and moving forward. Weather is really very variable. This is a 12-hour period. This is at the Solar Radiation Research Lab at the National Renewable Lab near Denver. And you've got a lot of variation here. The solar is the green and the brown, and you see some drop off in the afternoon. This is an August day, and they have a tendency to cloud up in the afternoon, so you'll see that. But we see wind speed changing throughout the day, temperatures changing as well. So we don't have this final resolution of data in most of the data sources we have today. Airports don't report that, and that is our largest source of data. There are some more higher res data sites, but not as many. Excuse me. New York Times has been creating these interactive pages that you can go in and put anywhere. And I'm sorry, I put Loughborough was not in their list of cities, so I went with London. London was 2016 globally was the hottest year, but in London it was actually slightly cooler. But what you see, if you look at some of these peaks, we're seeing way outside the range of normal. That's what the gray area is. And you're beginning to see a lot more in the swing months, the spring and the fall happening. When I look at other locations, we will see record high temperatures happening in those swing months, not so much in the summer. And that's pretty consistent with what we see there. So it was a particularly wet year. There were 24 more inches than normal in London that year. 2019 was the second hottest year, and now you begin to see those extremes really hitting there. None of them have hit a record that would have shown on this, but we are seeing things very much outside the normal temperatures in the low 30s for London. So, and it varies, and this is what you'll see if you start comparing it. This second hottest year, but if you look at Australia, that was one of the times that they were seeing temperatures 35, 40, 45 degrees, and the wildfires that were caused there in their summer. China was very hot. Africa was very hot. US and UK were kind of about normal. But it's not consistent there. Let's see, here we go. So this is kind of a look. You can see the temperature anomaly on the scale on the right. And so if it's below zero, it's a little cooler than normal. That's normal here is the 1951 to 1980 mean. So it varies. Pretty much all of the previous century was cooler than normal, the 1951 to 80 range again. But you see we have hot spots. Sometimes it gets worse. Sometimes it's cooler. The gray areas, there's no data, which is why they've done that. As we start to get toward recent decades, we begin to see that it's heading normal, which is what we would expect. And now as we move more recently into the 1980s and 1990s, you're beginning to see a lot of red. We are seeing that temperature anomaly already affecting that range. So you see even in some of these hottest years, there are cool spots. But 2016 globally, at least on the land, was the hottest we've seen. And so the 5 hottest years globally are in the last 5 years. Also seeing change in solar ice, polar sea ice, and what you'll see here in this chart, it starts off about 25,000 cubic kilometers of ice, and then by 2017 that's dropped almost in half. So we are seeing the effects already. We've seen temperature here, extreme temperatures. There were temperatures in the winter at the North Pole that were above freezing. It's never done that before, at least not in the record that they can see. Australia facing the wildfires and just the extreme heat. US on the East Coast in January, where we're seeing temperatures 10 to 15 degrees above normal. Global average temperatures, if you take that same data and look at it, we're already looking at a degree by 2020. And that's all those years that we've just been showing right there. 2020, kind of similar sort of range, and 2021, hot, but India in this case was colder. So it's not consistently where you take that. We look again at London. This is a great website, berkeley.lbl.gov, and allows you to put in your local, you can put in a lat long. This happened to put in for London, but you can see what's happening back in the history. Now there's uncertainty. The gray area there in the 1800s and 1900s is the uncertainty related to that. But on what you are seeing though is kind of consistently, by the time we hit 1980, we are beginning to head up. That temperature are up a whole degree from the 1980s to present day. London, the coldest months, the only recent ones you'll see for that are 2013 and 2010. But if I start looking at the hottest months, those are all within the past 20 years. So there's a lot of years, annual basis, except for 1990 there, the rank 7th, all of them in London are the hottest. High and low temperatures, kind of looking at the extremes. And again, we are seeing temperature change of somewhere around a degree, maybe a little less for the low temperature range. But we're seeing on the other side degree and a half on the high temperature side. So we're seeing both ends of that diurnal temperature change. If you're not aware about this book, it's a great book talking about building simulation. Particularly, it talks about everything from the basics all the way up to urban building physics and urban physics, and that's really useful. But I'm going to focus on weather and climate because I wrote the chapter. But so the book talks a lot about what it is we need climate data for, weather data, what are the specific needs, everything from doing simulation where you need a typical full year of data, equipment sizing, you might need short period calculations or design day, natural ventilation, you want to know local wind. Unfortunately, most of the data we have is not very useful for that from a wind aspect. Daylighting, we need to look at illuminance. Renewable, we need solar radiation. And some of that data is available, some of it's not, or not easily available. So air temperature, pretty easy to get. That's pretty universally observed. Humidity, tend to have that as well. Solar radiation is just rarely measured. There are only maybe 200 stations globally that collect solar radiation. And so that's kind of an issue for that. So most of the weather files that you see are have calculated solar, which you can trust or not. There's some new sources I'm going to talk about just in a minute, but other issues. By the time you get down to wind, it's very variable, even within a community, and it's poorly corresponding to what's there. And by the time we get down to precipitation, that's generally measured, but not maybe available always. So let's talk a little bit about climate availability. For many years, it was only available from the ground observing stations. The vast majority of those are for aviation. They're at airports, they're reporting temperature, they're reporting wind, humidity conditions to be able to deal with that. It rarely includes solar data. Other data can be limited or just missed entirely. There's remote sense data available today, satellite data. European reanalysis data set 5 is I think they're going down to a 9-kilometer grid. So they have taken the global data set and made it available in much finer grid. We're finding very good agreement with the ground stations. I'm doing a study right now, taking a look at several of those reanalysis projects with comparing them to the ground stations. The master data sets, US NOAA, the National Centers for Environmental Information, are providing data in near real time. Those are the ground observing stations. They are the repository of that data for the World Meteorological Organization. And that data set is good, but there are big gaps, and I'll show you some of that. But we can't just use the raw data. We need to do some calculations, statistics, if we're going to do design conditions. Generally, they've been based on historical record, but the ground observing stations also don't record solar, so we have some issues related to that. So design conditions, if you're familiar with the ASHRAE handbook and even the SIBSI guides have design conditions used for sizing of equipment, selecting equipment for various processes, not just buildings and HVAC. Usually you'll see dry bulb, wet bulb, dew point, and a few other variants on that at various frequencies. At least in the US, they're recommending using a 99.6, and what that means is 99.6% of the time, or about 35 hours, you can expect the temperature to be above that. So that's sort of what the percentile means on an annual basis. It doesn't mean that some years you won't have 70 hours, some years you may have 10. Same is true on the other end, which is the cooling. 1% means about 88 hours. that it's going to be hotter than that on an annual basis. Depending on what you're trying to do, other percentiles are available. You can use less stringent, more stringent. ASHRAE design calculations also recommends now using monthly percentiles, because what you'll see if you're used to doing simulations, that buildings often don't peak in the middle of the summer. They may peak late August into September because of solar angles and the temperature being warmer. So that's one of the reasons providing those. The best source is the handbook. Data for the SIBSI guide and other guides around the world are reproduced from this. The latest guide from last year, 9,200 locations. Remember when I started, there were about 1,400. So a lot of data's come online. This comes from that NOAA global data set. And we update it every 4 years, partly because it takes about 1.5 years to do the processing to make sure that we have it right. But it's the fundamentals handbook is updated kind of on that period. A study done in the 2009 handbook compared 2 sets of periods to look at what was happening, and what they saw was the heating dry bulb was increasing about 1.5 degrees in between those 2 periods, about a 20-year range, and the cooling dry bulb just under 1 degree. So we are already seeing that in the signal for that. Some of the trends you'll see as we're getting slight dependency. It's not consistent for every station. There are actually some stations that are getting colder for reasons we're not sure. It may have been a sensor change or other reasons, but generally there is a small significant dependency there. These are the locations in the handbook. Europe looks great. North America looks great. That little black dot, that's Alberta. Alberta has an agriculture meteorological station almost every 5 miles. So they almost have more than people in Alberta. And so they have a really rich data set. Europe is quite good. South America is okay, partly because there are not a lot of people in the regions where there are not any locations. Africa is a real problem. It has the WMO has a recommended density of collecting data, and Africa is about at 10% of what's recommended. The disturbing thing I found when I was looking, I did one of these DL trips to Lagos, Nigeria, and there were no weather stations in Nigeria for the largest economy in Africa. So it is kind of challenging. That's where the reanalysis data sets can help. We'll talk a little bit more about that. So in the new product that where you can get the data called WD View, it's now web-based. I can zoom in to the UK, zoom in a bit more to get to Loughborough. And so there's the East Midlands Airport. I click on that. I can then bring up the design conditions for that particular location. And so let's take a look at what information is here. These are available in spreadsheet format, but also PDF. So the top part are the annual heating, annual cooling, extreme conditions, which are based on statistics. And then we get in the next section, which deals with monthly data, where we have temperature, degree days, wind, precip, dry bulb, coincident wet bulb, etc., even down to mean daily temperature range. And then the last bit is clear sky solar radiance, which is useful in the design calculations and all sky as well. The last piece that's been added recently is this historical trends. For this particular station, there are no discernible trends for the station or any of the regions. Often I will see trends for cooling and degree days for some of these, but this is one of the cases where there isn't really a trend that you're seeing. one of the things that, let's see, is useful. This is NASA's reanalysis data set called POWER. They've pulled multiple satellite data sets together. These climate zones are used in the ASHRAE standards, and they're able to show you what how that's changing. So this one is from 2002 to 2011. You look kind of in the center, you'll see changes across there. So the climate zones are not static. I used to have a video to go in here. I didn't have one at this point, but you can see them changing year to year within their video. NASA Power just launched last August, a year ago August, and they have data from 2001 to present. The grid is somewhat coarse at about a half a degree. You can either give a longitude or pick it on a map. You can take a particular time period. You can get it in lots of different formats, including APW, to be able to use in simulation. Pretty powerful. What they've done here, that looks a lot like the design conditions. They're able to replicate the design conditions from the satellite within about a half a degree centigrade. So that's pretty useful. If we're doing climatic data, we typically have been using a typical meteorological year, which is an assemblage of different months that are each representative of that period. There's an ISO standard related to that. You'll see different versions of it, partly because they have different weightings of temperature, solar, wind, humidity, depending on what the use is. It's a statistical method based on the long term to see which is the best fit, and being able to find that for multiple regions. So there are lots of TMY data sets today. They're best for comparing alternatives during design. They're not terribly good for if you're trying to predict energy use. You want the actual data for the year to be able to do that. These are definitely not in that range. Often used for building codes and standards or rating systems to try to get there. There's no explicit effort to represent the extremes there, and they're not always representing design conditions. I've seen cases where they're quite mild. There are lots of data sets. CIBSE has, their set of 14 for the test reference years, and design summary years, and actual future as well, and long set available across there. I'll tell you a little bit about the last one as we get through to the end. Actual weather data. If you're trying to calibrate to energy use that you collected for metering, that you can do that to be able to set your simulation up. Lots of sources out there. You can use the data from NCEI, but then there are public and private organizations be happy to sell you the data for that. But part of the problem is making sure the data are complete. Does it include what you need, temperature, humidity, wind, etc. This is the longest continuous period of record I've been able to find. Happens to be the Washington, D.C. airport. It starts in 1938, and through today, we have hourly data available. There are many stations in Europe that had data back earlier than this, but there's a lot of missing data from 1945 into the 50s for those locations. The last bar on the right is the TMY, and the TMY does what it's supposed to do. It's not the extreme, and it's not extreme hot or extreme cold. So you get kind of a middle of the road sort of approach there, and that's what the TMY is doing. So what's happening? Again, the past 5 years are the warmest on record. The fundamentals are only updating every 4 years, so we've just now captured through 2019. So we're a bit behind. At least in the US, the TMY data sets are infrequently updated. The last update that we have, public data set was last updated in 2009, we updated through 2005, so it has none of that recent there. So I did a study for CIBSE Technical Symposium last year, I believe, and looked at some of the typical data sets out there and how they compare to what's going on. So I looked at 12 locations, and first starting off and seeing how within the different types of typical data sets, what we're seeing already. So this is an older, there's an older ASHRAE IWEC, IWEC 2, and then a recent data set that's showing pretty much uniformly we're seeing heating degree days are going down across 12 locations. It did not matter where it was, but what type. Even, yeah, you can see London, Gatwick, and Heathrow in there as well. Resolute being the coldest, it's above the Arctic Circle. Cooling degree days, maybe a little bit more extreme increase. The one outlier is Winnipeg. They're on the far right. I'm not quite sure why it's stayed kind of mild, but it has not increased very much. Resolute is there's no cooling. It rarely gets above about 8 or 9 degrees in Resolute. If we look at it from the degree days, or not the design conditions, you'll see this is a period of 24 years of the handbook changes. So if we go to, say, London, Heathrow there, what you're seeing is the heating design conditions have changed from about -3 to -1. So and we're seeing that consistently across all the data sets. If we look at the cooling side, we're again seeing that same thing. The one exception again is Winnipeg. It's just not increasing very much, but we're seeing kind of in the 1 to 2 degree changes in the design conditions. This isn't projected. This is from 1990s through today for that data. If we look at the energy use, trying to compare for those 3 sets, what you're seeing is not necessarily an increase, because we're seeing a decrease in decrease in heating that sometimes outweighs what the increase in cooling is. Particularly if you look at the next to last bar, Washington Dulles, the cooling is increasing somewhat, but the heating is decreasing more overall. So there is a kind of a big change there. If we look at just those heating and cooling uses, you are seeing almost across the board an increase somewhere in the range of a few percent or more, and then decreases in the on the heating sides. The other thing happening, this is Washington D.C. area. My house is right there. So we have this is Dulles Airport. This is National Airport. This is Joint Base Andrews. That's where Air Force One lives. Baltimore Airport's up here. What this is a study that NOAA did. They've been doing it around the country, but looking at what the temperature differences were on a particular day, looking at the heat island. And so this is a map they came up with for that. And what we're seeing is a temperature range of about 10 degrees between the coolest areas and the warmest areas. The warmest areas kind of here in the business core and the ceremonial core of the city. And then we have Rock Creek Park, which is a old growth forest that is actually a national park that runs through Washington, D.C. So it's a huge difference. So National Airport that I mentioned earlier is right here. And so it's somewhat moderated by the water, and you see that effect going up the river along here as well. So if I'm collecting data for National Airport or Dulles, how does it relate to the others? The answer is it usually doesn't. And so that's kind of, it's a challenge to be able to understand and have the data. As far as creating future data, there are a number of different methods. The first 2 are essentially very computer intensive methods, either downscaling the global climate model results or using stochastic modeling to create an altered frequency distribution of weather variables. one of the more popular ones, the one that's used by CIBSE, is the morphing technology. You essentially stretch and shift the data to be able to match what the future adjustment is. The other one is analog, and essentially analog scenario, you take a look at a climate that's predicted to be the same as, or let me start again. You look for a climate that matches what's predicted for the future and begin to look at. So these are kind of arrows showing the direction there. So the US, a lot of those locations are going to get increasingly hotter and more humid. This is, for example, Philadelphia, north of me. It is going to be like Memphis, Tennessee, which is substantially warmer than that. And so that sort of is kind of a challenge for that. But it's a useful way to understand that I could use Memphis weather today to see what the impact might be. The IPC climate change scenarios are kind of the basis for the morphing and some of the other techniques. They use 4 storylines that represent different social, demographic, economic growth models of what's going on. These are updated for each assessment report. AR5 was released in 2013. AR6 is not quite out. The data is available, but the report is just beginning to see the light of day. And their scenarios are called representative concentration pathways. And they sort of represent, they're not quite a temperature change, but they represent from the low to the high condition. So RCP 2.6, we do everything we can to avoid climate change. RCP 8.5, we don't do anything. We continue on. So the sort of annual temperature change predicted by them, you see the RCPs on the right side. You see the historical up through about 2005, and then the divergence there already. One of the things that's concerning is that we're already seeing temperatures at the 2050 level. That we're seeing temperatures already today that are there. So we're kind of ahead of the prediction. So that's going to be interesting. So if I take a TMY data set and I want to use morphing, I have an average monthly temperature change, a diurnal temperature change, usually a little bit squashing of the diurnal. Cloud cover can change, which will change solar radiation, and then precipitation as well. And what I can do is apply that to a file. My existing file here, this is for Los Angeles, and then there are 4 other lines there. They are RCPs. And the idea is to take a look at the base diurnal temperature and a scenario diurnal temperature. Often what you'll see is nighttime temperatures stay a little higher, so the diurnal temperature range is lower. And then we look at the temperature difference for that. So there's kind of a multi-dimensional way of changing that all at once. For heat island, I found some research which showed how that was, it actually is very similar to the climate change model, but it seems to be a function of city population. I think it's once a city gets so big, the heat island doesn't get any bigger. I'm seeing roughly 1 to 5 here. That's an average annual change, but as you saw on particular days, for Washington, D.C. and other places, you're going to see more extreme variation. Tends to depress daytime temperature. All the hard surfaces are absorbing heat for the day, and then as that's released after the sun goes down, it raises nighttime temperatures. So here's kind of another day. This is a spring day, Washington, Dulles again. The yellow line is the existing dry bulb, and so you'll see lower daytime temperatures just a little bit, not significant, but the temperatures tend to remain higher after sunset. This is based on several PhDs that I found when I was doing this work. And then they tend to remain higher until sunrise, and then the temperatures go back up. So you'll see a much smaller diurnal temperature range. So If I'm looking at, this is for Dulles medium office building, taking a look at what's changing. We've got 5 sets on here. We've got the TMY and 4 of the RCPs. And you see in Washington, we get cooling kind of starting in March and it goes into October. But if we go into the far RCP, what we're now seeing is cooling year round, a small amount of cooling. And heating is diminished quite a bit. So we are, that changed, and this is really where you see the biggest change in the performance. If we're looking at, this is kind of a different variant on this where I have a TMY, but I've also got a low and a high year where I'm looking at it. And from similar to what I showed earlier, that we're with the climate changing, the heating is coming down further than the cooling is increasing, partly because of efficiencies of the equipment. And so from a source energy, from the utility bill basis, we'd actually see slightly lower energy use. If we go to source energy, we are going to see increases, partly because the electricity has significant emissions at this point. Hopefully that's, we're going to transition to a clean grid, but at this point in time, it is going to be a few percent, at least in Washington. Other thing I looked at was taking what happens if we take a low energy building, and what you see is that heating and cooling are significantly less variable, and that's one of the advantages. We can mitigate a lot of that impact. Singapore is just going to be hotter. It's the tropical climate that's pretty much year round, and cooling is going to go up another overall 10–15% energy use. But low energy could take care of that. We could just completely mitigate the impact of that from just by building very efficient buildings. Toronto, kind of other extreme, little colder than Washington, a little longer winters, but the cooling is going to be significantly higher. If you compare the first set of bars to the others, it's on the order of 50% to 100% more in Toronto. And I think there are going to be a lot of locations like that are going to struggle, where they probably had very little air conditioning to begin with, and they're going to need significant. Northern Canada, this is that site up in Resolute, and you see there what's happening is it's showing a little cooling, but that's kind of in the noise. But the overall, that energy use is going to come down because the heating is coming down significantly. So if you look at this from a standpoint of, you'll see kind of the variation. Here's Cairo up here, upper left, and there is a little bit of heating kind of November to February, March in Cairo, not a lot. The temperatures can be kind of 18 and below that time of year, but you're seeing that cooling in the summer period is just growing a lot. Sao Paulo, Brazil, where there's, although it's showing a little bit of heating here, they don't typically do much heating in Sao Paulo. So what we're seeing is kind of a moderate amount of increase in the cooling. We already saw Washington, and there's Singapore again, but you see the variation there on a month-to-month basis. The one thing that I'm working on that I want to look at is what's actually occurring, not just the cooling and heating, but what's the full equivalent full load run hours for the heating and cooling equipment. Because what I think we're going to see is in some locations, it's going to double the amount of time that the equipment's running. And I think that may be more significant for us as engineers to worry about equipment that's going to fail a lot more frequently, because it's going to have to do a lot more. So in summary, we need climatic data. It's a key part of our doing building design, to understand what's going on in the climate, how our building can respond to that, and then how we can select equipment and systems. Typical actual and future weather are all available. You can get any of those available today. We've done some work on looking at what we call an XMY, or an extreme meteorological year, trying to find a way to say, from the period of record, can we select a set of months that would give us a more extreme cooling or heating condition? And we pretty well work. The method works. The problem is it does not work in a place that does not have a season, and that's Singapore. So that's a real challenge. We have rich resources of data. When I started my career, we had weather tapes, big magnetic reel tapes, and they were, you talked about your weather tape and you hugged it because there were only a few. Now you have thousands of data available. You can represent the climate change scenarios. You can essentially do whatever you need to look at that. We're going to see decreases in some of the higher latitude, partly because heating is going to decrease more than the cooling increases. Tropical and semi-tropical are going to bear the brunt of this. It'd be primarily increased cooling. We can mitigate this by low energy buildings. It can solve the heat island issue as well. But I think that the issue that I really want to investigate is how many more hours of cooling equipment operation are we going to really need? So ASHRAE has been involved. They've been publishing climatic statistics for 45 years or more, and the handbooks have been there to support the industry. They're producing trend data now to show how it's already changing. We're looking at seeing how we can deal with some of the future climate without picking a method or publishing data. One of the issues I have with using future climate in a regular design condition is that most of our buildings have very short lives in terms of their equipment. The equipment gets replaced regularly. It fails, so it has to be replaced. Somewhere between 10 and 25 years for most equipment. And so it's going to be changing. The other thing is our calculation methods for design sizing have a lot of slop in them. You'll rarely see a commercial building that will reach the full load predicted, that it may be operating no more than 70 or 80% of that equipment, and which is very inefficient. So the one thing we may want to look at is building envelopes, particularly because they are much longer lived than the systems within the building. But even they get changed out. In Washington, D.C., that corporate core of the city is they had 1960s construction, not unlike this building, and all the facades are coming off. They're rebuilding the buildings completely today. So it does change, but not as much. So the climate change impacts fuel and in-use swapping. We're going to see heating requirements down significantly, but including more cooling. So what should you do? Well, design the best building you can. Go beyond code, zero energy, zero carbon, if possible. It's a challenge yet. But remember, your components have a limited life. You want to minimize carbon-based fuel use, but you want to plan for upgrading. You need to be able to swap out equipment in the future. If you want to look at the next warmer climate. So here's some examples. San Francisco is going to be like LA, Boston like New York, Delhi like Mumbai. So take a look at what those climates are like, and do you think your safety factors oversized and be able to cover? And in real life, I think they will. So if you're doing building simulation, just use a future climate or from that next. So, and finally, small plug for work that I've been doing. Climate.1 building, there are weather files for over 15,000 locations globally. The data has been updated through 2021. So these are real recent data sets. They're available for free download if you're interested. And with that, thank you.
Thank you very much. Thank you. We are going to do the questions now, but before we do, we would like to give a little gift, just as a gratitude of our.
Oh, thank you.
Yeah, enjoy with your family. Unless you need it in an aircraft.
Yeah, right.
Okay, let's do
Let's
it.
come down. Let's take a quick photo.
Oh.
Let's take it.
Well, there's
The
going to be
next
our
class
IT.
is coming. The first slide. Yeah, that, not the first one. This one, yeah. See again.